Hello everyone, I welcome you all to Startup Academy, your online gateway to success in ISS exam. This academy is exclusively for ISS exam and we are focusing on ISS 2026. So we have been covering the topic sampling techniques. We have covered all of the econometrics according to the syllabus and now we are covering sampling techniques. Yesterday we did stratified sampling, a portion of allocations, and today we'll continue with allocations in the similar manner. So yesterday we did that there are four types of allocation: equal allocation, proportional allocation, Neyman allocation, and optimum allocation. And in optimum allocation, we did when cost was fixed and when variance was fixed, and minimizing variance and cost respectively for both the cases. So today we'll do the same with proportional allocation. Now we know that the formula for proportional allocation sample size was n I upon n into small n, which can also be written as wi into small n. Now, firstly, case 1, we fix cost to minimize variance. So let the cost be C dash. C dash is nothing but summation I goes from 1 to k Ci Ni. Now substituting Ni from above in here. Summation I goes from 1 to k Ci and Ni is Win. Now calculating the value of n from here, we will get n is equals to C dash upon summation I goes from 1 to k Ci Wi. And hence our value for small ni, in substituting in this equation, we will get Wi into C dash upon summation I goes from 1 to k Ci Wi. This is the value for Ni when the cost is fixed. Now for case 2, variance is fixed and we minimize cost. So variance is fixed. Let us take variance as V0, which is nothing but summation I goes from 1 to k Wi square Si square into 1 upon small ni minus 1 upon capital Ni. Now substituting again the values, V0 is plus summation I goes from 1 to k Wi square Si square upon capital Ni is equals to summation I goes from 1 to k Wi square Si square upon small ni. Substituting the value of small ni here, we will get V0 plus summation I goes from 1 to k Wi square Si square upon capital Ni is equals to summation I goes from 1 to k Wi square Si square upon the value of Ni was Win. Now getting the value of n from here, this can be cancelled one. So the value of n is summation I goes from 1 to k Wi Si square upon V0 plus summation I goes from 1 to k Wi square Si square upon Ni. This is the value of small n. and hence substituting this again in the first variable, first equation ni, we get wi into summation I goes from 1 to k wi si square upon v naught plus summation I goes from 1 to k wi square si square upon n, capital Ni. So this is the value of the sample size in proportional allocation with variance fixed and we minimize cost. Now moving forward, we will calculate the separate variances of first of all proportional allocation and then variance of Neyman allocation. So first of all, variance of proportional allocation. What is the variance of proportional allocation? We all know that capital N small ni is nothing but wi small n, and capital Ni is also like that, wi capital N. So variance of y bar stratified in the case of proportional allocation is summation I goes from 1 to k wi square 1 upon small ni minus 1 upon capital Ni into si square. Now substituting the value of small ni and capital Ni, we will get summation I goes from 1 to k wi square si square. Small ni is 1 upon wi small n minus 1 upon wi capital N. Now this wi and wi gets cancelled with 1 wi here, and we are left with summation I goes from 1 to k wi si square into 1 upon small n minus 1 upon capital N. So this is the variance of y bar proportional y bar st of proportional allocation. Let this be equation number 1. Now secondly, we will calculate variance of Neyman allocation. What was Neyman allocation's formula for Ni? Ni was capital Ni into Si upon summation I goes from 1 to k capital Ni Si into small n. This was the formula for Neyman allocation. Now again, variance of y bar st of Neyman is summation I goes from 1 to k wi square 1 upon small ni minus 1 upon capital Ni si square. This is the formula. Now substituting the value of small ni, we will get summation I goes from 1 to k wi square si square. Small ni is nothing but, now here small ni can also be written, if we divide above and below with capital N, we can also get wisi upon summation I goes from 1 to k wisi into N, because Ni upon N is nothing but Wi. So instead of writing NISI, we can write it as WISI N into summation I goes from 1 to k WISI minus 1 upon capital Ni. Now taking summation WISI square inside, we will get summation I goes from 1 to k WISI square into summation I goes from 1 to k WISI upon WISI into small n minus summation I goes from 1 to k WI square SI square upon capital NI. Now here one WI, one SI gets cancelled from here, and we are left with summation I goes from 1 to k WISI whole square upon small n minus. Now this Ni can be written as WIN from this equation. So WIN gets cancelled with one WI, and we are left with summation I goes from 1 to k WISI square upon capital N. So this is the formula for variance of y bar st of name and allocation. Let this be equation number 2. Now if we want to find the efficiency between name and allocation and proportional allocation, which is the best method out of the two, we will apply the formula variance of y bar st of proportional allocation minus variance of y bar st of name and allocation, which is nothing but equation 1 minus equation 2. So variance of y bar st proportional allocation was summation I goes from 1 to k WI square WISI square into 1 upon small n minus 1 upon capital N minus variance of y bar st name and allocation was summation I goes from 1 to k WISI whole square upon small n minus summation I goes from 1 to k WISI square upon capital N. This was the case. Now if I open the bracket, this capital N term and this term will get cancelled, and we are left with summation I goes from 1 to k WISI square upon small n minus summation I goes from 1 to k WISI whole square upon small n. Now taking out 1 upon small n common, and we are left with summation I goes from 1 to k WISI square minus summation I goes from 1 to k WISI square. Now this WISI, we can take WI common, and we are left with 1 upon n summation I goes from 1 to k WI bracket is SI square minus S bar square. Since one of the WI is getting out, and we are left with WI, which is nothing but Ni upon capital N, and when Ni gets multiplied by Si, this is nothing but what? This is S bar. Straight means every stratum's variance mean. So when if suppose n1 was the size of stratum 1 and s1 is the variance of stratum 1, and if we divide it by the total number of stratums capital N, then we will get the mean of stratum, which is s bar. So this can be written directly as 1 upon small n summation I goes from 1 to k WI into SI minus S bar whole square. Now this whole term is a positive term which is greater than equal to 0, and hence we can say that our variance of y bar st proportional allocation is greater than equal to variance of y bar st Neyman allocation, and hence we can say that Neyman's allocation is a better method or a better allocation method than proportional allocation. Similarly, if we want to compare with simple random sampling, now we know that variance of y bar in simple random sampling is nothing but capital N minus small n upon n into s square. This is the variance of SRS, and variance of y bar st of proportional allocation is nothing but summation I goes from 1 to k wi square si square into 1 upon small ni minus capital Ni. This is the formula. Now, first of all, we have to we have to find the relationship between Si and S. So, to express S in the form of Si, we will take the formula n minus 1 S square is nothing but summation I goes from 1 to k and summation j goes from 1 to ni yij minus y bar whole square. This is the formula for variance of stratified sampling. Now we can add and subtract y bar I in this term. I goes from 1 to k and j goes from 1 to ni yij minus y bar I plus y bar I minus y bar whole square. We can take these two terms common and these two terms together. Now this can be further written as n minus 1 s square is nothing but summation I goes from 1 to k summation j goes from 1 to ni into yij minus y bar I whole square plus summation I goes from 1 to k and summation j goes from 1 to ni y bar I minus y bar whole square. This can be written. Now here we can open j bracket on both the side. We are left with n minus 1 s square is equals to summation I goes from 1 to k. J is nothing but ni minus 1 yij minus y bar I square plus summation I goes from 1 to k ni minus 1 y bar I minus y bar whole square. This yij minus y bar I can be written as si square. That's why we have opened this jth bracket. This can be written as si square. Now moving further, we will divide the whole equation by capital N. So we are left with n minus 1 upon n s square is equals to summation I goes from 1 to k ni minus 1 upon capital N into si square plus summation I goes from 1 to k ni minus 1 upon capital N into yi bar minus y bar whole square. Now for large n, ni minus 1 is almost equal to ni, and n minus 1 is almost equal to n. So substituting that, we are left with n upon n s square is equals to summation I goes from 1 to k ni upon capital N si square, summation I goes from 1 to k ni upon n y bar I minus y bar whole square. So this ni upon n is nothing but wi, we all know that, and this n and n get cancelled. So we are now we will multiply. Okay, let us write it first. S square is equals to summation I goes from 1 to k wi si square plus summation I goes from 1 to k wi y bar I minus y bar whole square. Now we can substitute the value of 1 upon, we can substitute with this on both the side. Okay, so this is nothing but our variance of y bar of simple random sampling. This is nothing but our variance of y bar st of proportional allocation, and this is a positive value. So with this thing we can write that variance of y bar st of proportional allocation is greater than equal to, is less than equal to variance of y bar simple random sampling. From this equation and the previous one efficiency equation, we can write that variance of y bar simple random sampling is greater than variance of y bar proportional random sampling, proportional allocation is greater than variance of y bar st Neyman allocation. This question has been asked in the exam multiple number of times, that give the efficiency between simple random sampling, proportional allocation and Neyman allocation. This is how this question will be solved. Now moving on further to the estimation. What is the unbiased estimation of variance of n proportional allocation, optimum allocation, and all those? I'm doing just one. You can do the rest too. So variance estimation of variance of y bar st proportional allocation cap is nothing but estimation of 1 upon summation I goes from 1 to k wi si square 1 upon ni minus 1 upon capital Ni. This will be nothing but summation I goes from 1 to k wi square 1 upon small ni minus 1 upon capital Ni estimation of small si square, and this will again be summation I goes from 1 to k wi square 1 upon small ni minus 1 upon capital Ni si square, which is nothing but variance of y bar st of proportional allocation only, and hence variance of y bar st of proportional allocation is the unbiased estimator of variance of y bar st proportional allocation. Now we will similarly we can go for optimum, equal, and and Neyman allocation. You can do that on your own. Now what is the confidence interval? In case 1, when SI square is known. If SI square is known, then Z is equals to Y bar minus capital Y bar upon under root variance of Y bar ST cap follows normal 0 1, and hence 100 into 1 minus alpha percent confidence interval is given by pro- probability minus Z alpha by 2 goes from Y bar minus capital Y bar upon under root of variance of Y bar ST cap Z alpha by 2 is equals to 1 minus alpha. So we will get, what is the confidence interval? It is nothing but Y bar plus minus Z alpha by 2 under root variance of Y bar ST. Yeah, this is the this is the confidence interval when SI square is known. And case 2 when SI square is unknown. When SI square is unknown, then RT is equals to Y bar minus capital Y bar upon under root of variance of Y bar ST cap follows T n minus 1. Now here again 100 into 1 minus alpha percent confidence interval is given by probability minus T alpha by 2 is less than equal to Y bar minus capital Y bar upon under root of variance of Y bar ST cap into T alpha by 2 is equals to 1 minus alpha. So the confidence interval is given by Y bar plus minus T alpha by 2 comma n minus 1 under root of variance of Y bar ST. This is the variance. So this completes your topic allocation, and from tomorrow onwards we will start with new sampling. Your stratified random sampling is completed, and we have covered almost all the syllabus of stratified random sampling, and the PYQs are left, which we will do in the coming classes. Keep on working hard with consistency, and if you still have any doubts, then you can ask it on WhatsApp channel and in the comment box. Only relevant doubts will be answered. Thank you.